Good evening everyone, welcome to this British Geotechnical Association Early Career Group event. It's so great that you've come in person and thank you to all those who have also joined online. Delighted to be joined by Mark Pennington, who's here to talk to us about pile design from a contractor's perspective. Mark is a technical director at Balfour Beatty Ground Engineering with over 30 years of experience in the construction industry. He's spent the last 27 years working closely with piling contractors and has played a key role in developing practical and buildable piling solutions across a wide range of projects. So, could you please join me in giving Mark a warm welcome?
Thanks, Jack. There we go. Right. Evening, everyone. Thank you very much, Jack, for the introduction. So yes, I'm this evening going to talk about foundation design from a contractor's perspective. I think that actually means I'm going to talk about certain types of foundations that I'm more familiar with from my own personal viewpoint. So hopefully you agree with that, and hopefully that ticks the box for what you're expecting to hear today. So I'm going to do that. I'll set the scene just to start off with a little bit. I'll explain a little bit about me. As I said, this is really from my perspective and my experience that I'm giving you this talk. I'll run through a few different foundation solutions and then focusing in on the ones that we're going to cover today, which hopefully will explain the thought process I'm going through. I then want to cover reducing ground risk. I think that's a fundamental element of any foundation design or construction, to be perfectly honest. We're working with a non-homogeneous material. We're either working in it or on it, and we have to manage the risk of how we're working on that. So that's really the basis of any foundation design or construction, to get that all working together. I'll then move on to certain types of pile foundations, which I'll cover in a bit of detail, which hopefully then leads on quite nicely into embedded retaining walls, which then leads on into basement construction. And I use all of those to link together to share the differences between some design decisions and construction decisions. So firstly, a little bit about me. Jack's already mentioned some of this. So 34 years in geotechnical engineering. First 7 I spent with a consulting engineer, which was very nice. It gave me a good basic grounding of geotechnical design. It also gave me the opportunity to become chartered, and I think presenting in this very fine institution was something very key and important to me, and still is, to be perfectly honest. So that was good. I then moved over from a consultant to contracting. I've worked for 2 different contractors, firstly working for AMEC and more recently Balfour Beatty. Now both of those contractors had OPCOs, operating companies, as part of them, which were foundation companies, and I've always worked in the design side of those individual operating companies. So I've stayed quite close to design of foundation solutions, either designed by the contracting organisation or working with consultants on projects where the contractor's not having the design responsibility. And it's that experience which is thrown up certain sort of key decisions or key issues that have continued to arise, and they're the ones I want to run through a bit today. The last 10 years I've been technical director with BGA. That's given me the opportunity to expand a little bit beyond technical. A bit of quality and a bit of digital is something under my remit at the moment, and I think both of those areas are key and are developing and continue to develop and have an influence on the type of foundations that that we use and that we build. And 4 years ago, I became a fellow of the Institute of Civil Engineers. That's a bit about me. This here covers some foundation solutions. Now, if we take out some of the basic shallow foundations, if we're looking at pads or strip foundations, I think that foundation design can fit within 2 main categories. We've got pile foundations and we've got ground improvement. The third one I've got there in the box is some specialist techniques, which I think feature in or feed into both of those. So the difference between piling and ground improvement. Piling generally puts a structural element in the ground, which transmits the load from whatever we're building, whatever structure or whatever we're putting on top, directly through that structural element down to a more competent strata. Whereas ground improvement, you put some element in the ground and it works with the ground, so you use the ground support as well as the element you're putting into the ground to support whatever you're putting on top. So in some respects, you may say, well, ground improvement's a much more efficient way of doing it because you're using the ground as well as the elements, but you can't take as a higher load and you get a bit more movement with ground improvement. So it is horses for courses, and it's using the right solution for the right idea. I'm going to be covering today, concentrating really on piled foundations, because piled foundations is my background, so I'm going to run through some of the main elements of piled foundations and look at both the design considerations and the construction considerations that feed in to the piled solutions. A lot of piled solutions are covered there in the left-hand box, and they can be split really into two types of piles. You've got displacement piles and you've got replacement piles. So displacement piles, where you're putting a piled foundation into the ground, where you're not really taking any spoil out of the ground, you're putting a pile into the ground which displaces the soil that it's going into. So this is more like a driven pile or an augered pile that doesn't actually take the ground out. A replacement pile, you're excavating the ground, the soil or the rock, and you're replacing it with a material, normally concrete, to create a pile. And I'll cover those two different types of piled solutions in a bit, looking at some of the key benefits and some of the key considerations that I think we need to think about each time we look at those foundations. Right, so moving on to geotechnical risks. This is quite a busy slide here. And I do have to admit, I did have Copilot help me produce this slide and had a bit of fun playing with that. But it does cover some of the key aspects around geotechnical risk quite well, I think. And I'll walk around it quite slowly and cover each item in turn. So a lot of the, a lot of the decisions or risk management, I think, can be split into these 5 areas. And there's a lot of facets which come into each of these 5 areas. So top left there, we've got sustainability. Now, sustainability is something which is becoming more and more important in both the design and the construction of any foundation solution. I'm currently involved in Lower Thames Crossing, and Lower Thames Crossing is a project which is being built, and we can see it happening as being a project where sustainability decisions will override any other decisions that are made around the foundations that are being used on the project. So we'll see how that develops and see what see how that moves forward. But definitely, there will be more and more as we move forward that foundation solutions will be chosen based on sustainability credits, so sustainability marking. So the sustainability team has a significant impact in both the design and construction solutions. Second one is temporary works. Temporary works comes in many different types. Later on, I'm going to be moving on to basement construction. We're talking about how basements are built. There are 2 main different types of basement construction, a top-down or a bottom-up construction. I'll cover those in a lot more detail later on. But whether you use a top-down or bottom-up construction has a significant impact on the temporary works that you might need for that particular foundation solution. Or it may be something as simple as the piling platform that you're using, or platform you're needing for any kind of foundation equipment that you're using. The design of that platform may influence the type of foundation you're putting in the ground. So temporary works has a significant impact. We've got what I've termed the lifting team there. The lifting team is quite a broad term. It's any kind of lifting that's taken on around foundation construction. So you can have piles as we move on to, or foundations which are manufactured off-site and brought into site. Again, you've got to consider how they're lifted into place once they get to site. Or you may have a lot of stuff fabricated actually on-site that needs to be lifted and put into position. So how those things are lifted and actually constructed is a significant input into how the foundation or the right foundation solution is taken. I think logistical planning is quite obvious. Again, a lot of foundations are built with very large pieces of equipment. A typical piling rig could be 100 tons or more moving around the site. People-plant interface is one of the biggest safety risks we have on foundation construction sites when we're looking at it. So how the logistical planning of a site is set out and what area there is to work on is significant. If you're working, for example, on the side of a live motorway, you might have a very small amount of space to work in. That will influence the type of foundation solution you can have, rather than working on a big open greenfield site. So again, your location of where you're working may drive the type of solution that you're thinking about at the front end. And then that all comes back to the design team. So at the front end, you'll have a design team looking at a design solution for a certain type of foundation, and they have to really take into consideration a lot of these points before the contractor gets involved, and then again when a contractor gets involved in any design solution, so they can all work together. So I think if you have a good combination of all of these, and all of these work together in a utopian world, you will get a good foundation solution. And some sites, some may be more important than others. So in some ways, the design may be the critical element of the solution. In some areas, the logistical planning may be the critical area. And it's very difficult to say until you actually start looking at the site. But they all need to play a part in one form or another. Okay. So with that in mind, I'm going to move on now to a bit of pile foundation solution. So here, this follows on a little bit from the slide we just had there around managing geotechnical risk. There are a number of influences there on pile choice that I think you can read and you can look through, and some of them may be really quite obvious. I think one there that I've put in, which is quite key, is down at the bottom there, personal preference. So it may well be, you've got people that are working on projects and involved and making decisions on projects. They have a personal preference around the type of foundation solution that they want, and that may have a significant influence, and everything else just has to work around it. So you've got to work out how your logistical planning and your sustainability options work. If you've got somebody who particularly wants that type of foundation solution in there. But there are, again, many things that influence that that type of piled, any type of piled solution. So I'm now going to run through 4 different types of piled solution: 2 displacement and then 2 replacement piled solutions. I'll run through driven piling and steel piling, and then a continuous flight auger pile for a replacement pile, and a large diameter rotary pile. And I'll look at some key benefits and key considerations that need to be made on which type of pile foundation you might choose. So we start off with the driven precast concrete pile. These may seem as a very good solution because they tick a number of boxes. If you think about a sustainability box, these are manufactured off-site. They're a factory product. You can see them before they get to site. You can use quite efficient concrete. It has on there is some waste, but there's minimal waste if you can drive these piles correctly to the right depth. So they're very good and a useful foundation solution. You don't get any spoil coming out from them. They're a displacement pile solution. So you just drive them into the ground and there's no spoil that comes up. Typical sizes for these are only up to around about 400 mil square at a typical maximum size of a precast pile solution. And that's really because of how they're manufactured, how they're cast, how they're lifted, and how they're delivered to the site. You get bigger than that and you start to get unpractical around the size of pile you can actually lift and then drive into the ground. But that itself then has some limitations on the load that you can put onto those those piles. So you can get an efficient pile solution in there, but it does have a limit on the amount of load that you can transmit from your structure down into the ground. Another key element I'd like to highlight on this is self-proving. So with a driven piled solution, and it's the same as this one, and for the steel piles, which I'll move on to in a moment, you drive a pile into the ground, it would normally hit a set, it would normally hit a capacity, so it's got a good load carrying capacity because you've driven it to a certain to a certain set. We call it a certain number of blows, which is a certain amount of settlement in each of the piles. So you're really proving that pile's capacity every time you drive it into the ground, and that's quite a fundamental part of reducing geotechnical risk. If you can put a precast pile in the ground and prove it's actually got that load. Some points to consider around precast piling: Clearly, it makes some noise if you're driving a pile into the ground, and it creates some vibration. So that might have an impact around the location you could use a precast pile in. I've covered the limited loads and as a potential waste. If the piles don't dry, you drive them to a set and you get piles sticking out of the ground, you have to crop them off, and then you've got effectively waste concrete, which you can't do anything with. Jointing precast piles is actually a lot more straightforward than the steel piles, which I'll move on to in a moment. So if we move on to steel piles, there some of the benefits, I think, and some of the considerations are very similar to the precast. So again, it's a factory manufactured pile, so you can see it before you drive it into the ground, so you know that it's good and has good quality. You can drive slightly bigger sizes with tubes, and you can drive them a bit harder because it's steel rather than concrete, and so you can get a bit more load out of steel piles. So if you're wanting to get a higher load capacity out of your driven pile, you want to be moving to a steel pile rather than a concrete pile. And they're also less prone to breakages. I didn't mention for the precast piles, but precast piles an issue if you hit obstructions or you hit some hard ground. There is the possibility that the piles can break during the driving process, and then replacement piles have to be put in. Steel piles are much better than that. You can drive them a lot harder to get them into the right position. Again, I think the self-proving, no spoil are the big wins on steel tubes. I think the key point to note on the considerations about steel tubes is around the jointing. So again, they're not as easy to join as the precast piles. Precast piles, you can actually have steel joints where you can put on top of one pile and join another pile to it. Here, it's a lot more welding typically is carried out to join piles. So if you've got piles which are longer, then you can typically deliver to site, and deliver to site something like 18 metres long is the typical size maximum length you would deliver to a site. If you're looking at driving longer than that, you're going to have to think about joining the tubes as you drive, and that might involve quite a lot of welding, which could have a program impact. Well, so that's a whistle stop of the two replacement types of pile I wanted to discuss. If we move on to the two types of replacement pile I want to run through. Firstly, we've got the continuous flight auger piles. So these are piles which are constructed using, as the title says, a continuous flight of auger. So you've got a full length of auger on your piling rig. You drill that down, as in the top left, into the ground, down to the desired depth that you need. You then pump through that auger, through the hollow stem in that auger, your concrete, and then as you extract the auger, the concrete is placed into the ground. So it's a very neat replacement pile because it's fully supporting. You've either got the auger in the ground or you've got the concrete in the ground supporting you're supporting the ground as you're building the pile. You would concrete that up to the ground level, up to your piling platform level with the concrete, and then you plunge in your reinforcing cage to the desired depth, and then you can finish your pile off at the top. And so again, it's a good neat technique because it is efficient and it supports the bore. There are certain things to consider here. Obviously, if you're putting a full auger into the ground, you have a limitation on the depth you can get to and on the size of the auger that you can use. Size of the auger primarily because of the torque of the machine that you can actually turn the auger into the ground, and the depth really based on the size of the auger that you can get. So here we've got a maximum depth of 34 metres, which was typical. I think I did read in some publication recently that somebody's put a pile into 40 metres recently with CFA. So again, that's all basically by increasing the size of the rig, increasing the torque of the rig, and depending on ground conditions, you can get to, I say, somewhere between 30 and 40 metres with CFA piles. The limitation on that, the two key limitations on that, I think from a constructability perspective that keep coming up. The first one is the reinforcement is put into the pile after the concrete's up at ground level, so there's a limit to the depth you can get your reinforcement, plunge your reinforcement into the concrete. So you may be able to put a pile to 40 metres depth, but you won't be able to plunge your reinforcement to 40 metres depth if you're putting a cage in. More typically, you put a cage in your pile to about 20 metres. So if you're needing to reinforce your pile full depth down to a 40 metre length or that kind of order, CFA won't be the technique that you will really be looking at. The second key point on this is that you finish the pile at the ground level, at the level you're piling from. So there are many instances where you're piling from a level and you want to excavate a basement or excavate down below that for one reason or another to get down to your actual construction level of your pile, but you need your concrete in CFA to finish at ground level. So you'd have to break that pile down to the level that you need to get to. So those considerations just need to be made when you're choosing a pile foundation at a design case. And the final thing to mention maybe is around, very different to a precast pile or a steel pile, is that it's a blind, it really is a very blind piling method. You're putting an auger in the ground, you're taking out, you're concreting the pile. You don't really know what's happening with that concrete. There's a lot of instrumentation on CFA piling rigs now, which show the amount of concrete that's going into your bore to make sure you've got the right kind of concrete filling the void, filling the pile that you've excavated, but you're reliant on that. Instrumentation to ensure your pile's right. So the second type of replacement pile I want to discuss is a more standard rotary bored pile. So in this technique, you can see here you will typically put a casing in the ground at the top to support the ground at the top. You would then put an auger in the ground, and the auger is more like a metre high here on the end of a Kelly bar. So you put an auger in the ground, it would take a bite of the spoil, you bring that back out, spin the spoil off, and keep digging down with your effectively your bites or your auger as you dig down into your pile. That means you can get to much deeper depths. There's no real limitation on the depth. We've got 80 metres there, we've noted, but it could be longer than that. It's all relevant to the Kelly bar that you've got on your rig, and the Kelly bars extend. So you can dig much deeper. If you're in ground that supports itself, you can also see down the pile. So you can dig a hole, you've got an open bore, you can actually visually see down the pile. If the ground isn't supporting as you're digging below your casing, you may need support fluid, a bentonite or a polymer to put into that pile as you're excavating the pile down to depth. And then obviously you've got the polymer or bentonite in the pile, you won't be able to see down the pile, but you would know that your auger's continually going in and out. So it gives a lot more flexibility, I think, a rotary bored pile, but it's typically slower than CFA, but it can deal with a lot more ground conditions, and there's a lot better to deal with things like obstructions. So you dig your pile down to your required depth, with or without your support fluid in. You clean your pile. You would then put in your reinforcing cage into the pile down to whatever depth you need to. You could put a reinforcing cage and join it as you put it into the pile. So you could put reinforcing cages much deeper into rotary piles than CFA. And then you would tremie in your concrete into the pile. So you put a tremie tube down and you'd concrete the pile. So a consideration there is obviously the concrete needs to flow through the reinforcing cage as it flows into the pile. So the reinforcing cage needs to be designed with enough space, enough gaps in it to allow concrete to flow through the reinforcing cage to the outside of the pile to make it work. So again, a key consideration that's needed in the design process. A rotary bored pile really can go through any ground conditions, I say, if you've got the right support fluid and the right technique. So that's just a few pros and cons, I think, or benefits and considerations I've got around those 4 different types of pile methodology. So those piles can then be used to form embedded retaining walls. So again, you can form a pile just to carry vertical load. You can use a pile to put a retaining wall in, so you can then excavate in front of that. And I'll run through a number of different types of embedded retaining walls, and then I'll concentrate very much on diaphragm wall construction. I think that's because that's the most complicated of the embedded retaining walls, and it covers a lot of the impacts from a lot of the other, a lot of the risks that are associated with a lot of the other methods, I think. So firstly, I'll cover sheet pile walls. I've got standard sheet pile walls. They can be driven in, they can be pressed in, they can be vibrated in. They come in different shapes. We've got here a U pile or a Z pile. They can be clutched together, so you can. It says here they're not water retaining, but you can get them if you can sort the jointing out adequately. You can get them to be pretty water retaining, to be perfectly honest. There can be issues around obstructions in the ground as you're driving or pressing these in. There may be some need for pre-boring, but they're a very efficient and relatively quick way of forming an embedded retaining wall. The other benefit with a steel sheet pile is they can be removed. So you can put them in, you can have, if it's a temporary excavation, and then you can potentially excavate them or take them out of the ground. So again, a very quick and useful embedded retaining wall solution. The second one's a king post pile wall. So here we can see we've got H piles, which are typically put into a rotary board pile. You normally put a rotary board pile into the ground. You then plunge an H pile into that, and then in between your H piles you put some kind of a it could be timber or steel lagging in between it to form the wall. And this can be done as you excavate down your basement. So again, it's quite a quick and easy embedded retaining wall solution. Not used greatly in my experience within the UK, particularly for permanent works. There are some temporary works and fairly small excavations where you could use this kind of solution because it is quite quick and easy. Understanding in America this is used quite frequently for lots of their basement excavations, but it's not a common, it isn't a common retaining wall within the UK. Again, that's only based on my experience. Other people may have different views. The pile walls, or the replacement pile walls, which are very common and used quite frequently within the UK, are either a contiguous or a secant pile wall. So a contiguous pile wall is built by putting effectively individual piles next to each other, typically at a spacing of 100-150 millimetres between the piles, and these are built just as individual piles constructed along a length of a wall. Because they're not interlocking, they're not touching each other, they're just built like individual piles, so sequencing isn't really an issue for a contiguous pile wall. And again, so they can be constructed relatively, relatively quickly and easily, but they can form, as we can see in some of these pictures here, some quite neat and deep excavations in the right ground conditions. Again, it's not a water retaining a wall in any way, shape or form, and can really be only used in material that can support itself in between the piles. These type of piles can be used, can be constructed using the CFA technique we've spoken about, or the rotary board pile technique. So you can put a contiguous wall in with either CFA or rotary board. Again, you've got to think about the CFA solution, the depth of the reinforcement that you're likely to need within the pile. And also, the difference between CFA and rotary techniques for constructing these piles will be the tolerances. So a rotary board pile, which is constructed with a piece of casing typically to start off with, has a better tolerance than a CFA pile. So again, if you're looking for basement excavations really over something like 7-8 metres depth, you're wanting to be thinking more of a rotary board solution, I'd suggest. Moving on to the second type of retaining wall, replacement retaining wall is a secant wall. So here you can see that we're getting, starting to get a little bit more engineered and a little bit more detailed. This can be designed to retain water. It can look at it has an interlock between the piles. So these walls are constructed by firstly constructing the the female or the primary piles, as they're called, and these female or primary piles could be either constructed from a soft mix, a cement bentonite kind of mix, which really doesn't get very hard, or it could be constructed with a firm mix, where you get a concrete up to something like an 8 or 10 Newton, or they could be constructed with a full concrete mix, where you get a typical strength up to your normal 30-40 Newtons. The difference between those from the female piles and whether you have a soft, a hard, or a firm is that the final use of the wall will play a big impact on that, but the constructability of the wall also plays a fundamental part, because once you put the primary piles in, you then bring your male piles in and you cut into those female piles to create the interlock and to create the water retention parts of the wall. So the harder the female piles, the harder the primary piles you put in the first place, the more difficult it's going to be to construct your secondary or your male piles. Again, these piles can be constructed using a CFA technique or a rotary board technique. Either can be used to construct a secant pile wall. Again, because you're cutting into piles, the harder the concrete and the deeper you're going with your female piles, the more likely it is you're going to look at a rotary board technique, because again you've got a bit more flexibility in the constructability of those walls. The picture on the left-hand side there shows a guide wall. So again, it's very typical for these piles because of the need for the interlock of the piles. You construct a guide wall which guides the piles in at the top end of the wall. So you're certain of the interlock you're getting between the two piles. It starts the piles in the right place. And so that's a bit of temporary works that's needed at the front end in order to build your secant pile. And just looking at the picture at the bottom, we can have reinforcement or not reinforcement in the female piles. Again, in my experience, it's really typical not to reinforce the female piles unless you really have to. You can put as much reinforcement as you can into the male piles, depending on the technique you're using to construct them. And so the female piles can be left just really as a span between the male piles. So all the structural work is done within the female piles. And again, my experience is that it's a hard, firm wall are the walls that are typically used in basement construction. They're the ones which are commonly used going forward. Okay, is there anything more on secant piles? I don't think so. Okay. So I'll move on now to diaphragm walling, and I've got a bit of detail here on the construction of diaphragm walls, because again they're a bit more there's a bit more detail around these and how they're actually built and constructed, and a little bit more constructability issues that are needed around rather than the design, if that makes sense. So a diaphragm wall can be constructed using a grab, which is a picture on the left-hand side there, where material is grabbed out of the ground in bites, a little bit like the rotary board piles were, or milled, as the picture in the middle there is showing, where the ground is effectively turned into a fluid, basically. So the mills come in and it turns the ground into fluid, and then it's pumped out as you're digging the panel. And the picture on the right shows a completed diaphragm wall, which was constructed with a grab. So I'm going to go through and just cover the process behind constructing a diaphragm wall with a grab, but a very similar process can be adopted for the mill in the middle. The difference really you'd use for the grab and the mill is more applicable in harder ground. So if you've got a harder ground where grab might not physically be able to grab out the material, the mill would be able to cut into that material, make it into fluid, and it can be pumped out. Most stuff in the UK is grabbed, to be perfectly honest. There's recently stuff on High Speed 2 where we've gone down into the mudstone, where mills have been used more frequently. Okay, so the first thing that's needed to be done with diaphragm wall construction is the installation of a guide wall. And again, this is a little bit like the secant pile wall, that you need to be able to line. You need to be sure that your diaphragm wall is constructed in a straight and consistent line. And so by putting a guide wall in and two concrete walls either side, allows you to make that happen. It also serves as a couple of other purposes. It serves as a measured level you can trap your reinforcement cages on to make sure your reinforcement cages get it stopped at the right level into the excavation, particularly if you've got starter bars for slab connections in the wall further down. So, and it also, you can mark out where your different bites and where your different panels are going. So it's quite a significant element of temporary works that's needed for diaphragm wall construction. Once your guide wall's in place on the site, you can start your construction. It's typical that you will build a panel either as a single bite or a multi-bite panel. If you're building a multi-bite panel, it's typically 3 bites. So you dig your first bite down with your grab down to the required depth, and as you're digging down, you will fill the excavation with bentonite. So we can see, you'll see there's a bentonite feed which will come in a moment, which will be fed continually into the panel. There it is, and there's a significant size bentonite plant that you might need on your site. So again, this all links very much back to the reducing your geotechnical risk. You've got quite a lot of temporary works to think about, and you've got a lot of plant and logistical planning on site if you're looking at a diaphragm wall. We can see here for this multi-bite panel, you've got 2 bites that you do. So you do a first bite and a second bite, and leave a little, bite in the middle, and that you come to clean out your panel. The key point about that is that really then drives the width of the panels that you're constructing each time. So typically grabs are 2.8 metres wide, typical grabs, but they may not all be like that. There may be some which are 3 metres, 3.1 metres we've used, but typically 2.8. So if you've got a 2.8 bite, that gives you 5.4 metres. You'd leave a bite in the middle of 800 to a metre, so that gives you around about 6.5 metre panels. And this is quite fundamental, that it's difficult to change that if you're using grabs of standard size. You need to be able to construct your panels at that kind of that kind of width as you build the wall. And so that does influence, as we move on now to the reinforcement design or any kind of propping design that you may have linked to your reinforcement. So you can't say, well, let's have a 6 metre panel or a 5.8 metre wide panel typically around the wall, because from a constructability perspective, that's very difficult to achieve. So once you excavate your spoil out, take it away. Once you've dug your panel, you have to put some jointing elements in at the end ready to join onto your next panel. So these are typically, this here is shown, which is a typical CWS stop end, but there are different types of stop ends you can use, that you lower these basically down into the ground at the edge of the panel that you've just excavated. And you trap them off again using your guide wall, temporary works guide wall, that you constructed earlier on. You can see here we've got the steel stop end, and in front of that there's a blue element, that's the water bar. And so there's typically a water bar which is put in, which we'll see in a minute how that's left in place when you remove the stop end to provide an additional water stop between the panel joints. So that's, I say, a different way of just helping the water, the water resistance of the wall. But again, you can see the size of these stop ends, and you can see logistical planning of the site. Again, you've got stop ends to deal with on site, as well as the next phase of works, which is the reinforcing cages, which are delivered to the to the site. So you put the stop ends in, your then reinforcement will be delivered by and typically manufactured off site. So you can see that it's in the right place. You bring it to site and lay it down on the floor, so you need enough space to be able to see it. This here is a pit we've put in. This was used as a training video as well. A key part of this is checking for loose bars within the cages, because typically when you bring a cage to site, the first time you turn it from horizontal to vertical will be on site live when you're about to drop it down into the diaphragm wall panel. So cages are manufactured flat, they're lifted flat, put onto a flatbed, driven to site, and then offloaded flat, and then turned up onto the vertical before it's lowered down into the panel. There, so the panel's still filled with the bentonite or polymer support fluid. You can see the polymer support fluid farm on the left-hand side there, the tanks, and which takes up a good bit of space. Again, typically you would have a typical diaphragm wall could be anything up to 50, 60 metres on there, could even be more than that. And so if you're bringing your cages in lengths of 18, you'd have to join them as you're lowering them down into the cage. And that's just done by splicing these cages as you lower them down into the panel. Once they're at the right level, or you drop them down, you trap them off. There's, you see, trapped off, and different ways of trapping are shown there against the guide wall. So the panels are then, the cages are then down in the ground and hopefully trapped off at the right level. And you can get those really quite accurate. And designs will need them, because if you may have starter bars in those reinforcing cages which link into the slabs which will connect into the diaphragm wall during the excavation, and those need to be in within plus or minus a few tens of millimeters, and so the trapping off of those cages has to be at the right level. So the guide will cast to a certain level. You can then measure how you're trapping your cages off as you put them into the ground. So once your cages are in place, you can then start bringing the concrete into the panel. So again, you lower these down with a tremie tube, which is again trapped off. Again, more bit of temporary works here. You've got cages over the top of these panels platforms over the top of these panels, because you've got basically a great big hole filled with a support fluid, which is quite dangerous to be walking around and getting anywhere close to. So there are temporary works platforms which is designed to sit over the top of these, and so you can safely concrete the panels. And as the concrete is poured in through the tremie tube, as we should see here now, hopefully you can then start, concrete is poured down the tremie tube, which then displaces the support fluid, the polymer or bentonite that's in the panel. That's pumped back out to the polymer or bentonite farm, and your tremie tubes can be gradually lifted and split as they're coming out of the ground. So you always need to keep the tremie tubes embedded into the concrete, but you only need to have them embedded adequately or enough to ensure you can continually get flow of the concrete. So effectively you continue that to concrete your panel all the way up to the top. Once you've constructed your first panel in the ground, you can then start thinking about constructing your second panel. So again, you'd carry on with the now running panel, which has these 3 bites again. So a similar kind of width panel, 6.5 meters. You build the bite furthest away from the original panel you constructed. Then you build one close to, and then take out the bit in the middle. This is where you now lift out your stop end. So you can remove your stop end that you put in from your previous panel and leave your water bar in place. So that water bar will then provide a connection between the 2 panels, and effectively a bit of water resistance through the joint you've got between those 2 panels. So sequence is a fundamental part of, or key consideration that needs to be taken into account with diaphragm wall construction. You don't really want to leave your stop ends in too long before constructing your next panel, because they start to get concreted in, and they start to have, the longer you leave them in, the harder it is to get them out. So you have to try and plan your sequence of works around so that you've got a number of different number of different areas you're working on, number of different fronts, effectively, you're working a diaphragm wall from, so that you can complete your panel and remove your stop end in a tidy manner. Again, you carry on with your concreting, and you concrete around the site on these different headings that you would have, until you get round to your closing panel. And again, you might have more than one closing panel on the site. You'd have a variety of them, where you would then come in and start your excavation for your closing panel, remove your 2 stop ends now that you have in on both ends to complete, effectively to complete the wall. So hopefully this is highlighting, just with this little sequence, some of the considerations that are taken into account with this kind of replacement embedded retaining wall construction. And if it's not a diaphragm wall, your secant wall follows a similar kind of process, or a similar kind of sequence, and a similar kind of logistical planning at the ground level. So choosing the right type of wall for the right type of circumstances is key. The other thing to think about with retaining walls is managing expectations. So we've seen the wall there constructed from ground level. It might be constructed, down to 40, 50, 60 metres below ground level. You may be excavating down in a basement to be, it could be 30 metres or it could be more. So you're building a structure 30 metres below the level that you're looking at, you're starting from. So you're not going to expect it to be perfect. You're expecting that it's going to be cast against the ground, and it's going to need a bit of what we like to term finishing works at the end of it. So people should be aware that as you're digging down, you will have some damp patches. You're likely to have a few leaks that are coming in on the wall, and I think this is normal around a embedded retaining wall construction. So again, it should be considered as part of the design considerations, I think, that you have around how you're looking at embedded retaining walls and what water retention you need at the end of the day. So they only provide a certain level of or a certain class of water retention. And I think if people's expectations are managed around what walls look like when they excavate, they're happy with it. If people are expecting a perfect wall finish, they get a bit disappointed when they start digging down. Okay, so that was a quick trip around, or a quick scan through diaphragm wall construction, and hopefully that links back to the slide we had around managing geotechnical risk, and you can see the number of aspects that were all combining together to be able to make that wall work properly. Diaphragm walls, or secant walls, or contig walls, or sheet pile walls can all be used in basement construction. So you can have basement construction where you're putting an embedded retaining wall around the site, and you may have piles in the middle to support a structure. So again, there are a number of considerations to think about when you're then moving on from building that wall and taking it into a basement construction kind of a scenario. So a number listed here. I think some are really quite obvious, around program, around price. These are going to be key considerations, logistical. Some may be, a bit more surprising. The neighbours, the noise, vibration, the methodology that you're using has to all be taken into consideration. And again, you start getting to some of the key points here around embodied carbon, so the sustainability considerations are all taken into account. But one of the key questions that you'll ask at the front end of a basement construction are whether you're building this basement construction as a top-down or a bottom-up. So I mentioned this at the front end around the different type of temporary works you need. So a bottom-up construction is effectively putting in your embedded retaining wall, and you would excavate down to your final excavation level in your basement using temporary propping to get down to that level, and then you build your superstructure, your structure from your basement level up. So you're building it from the bottom of the excavation up. Whereas a top-down construction looks at building the ground floor slab, so typically putting in some temporary plunge columns, which I'll come on to in a moment, plunge columns which are built into the are put in from the ground level. You then support your ground floor slab on top of your plunge columns. You can then excavate underneath your floor slab as well as building your superstructure at the same time. And so there are very different temporary work solutions that are needed there, and it's all very dependent on the on the program, the price, the requirement to get the superstructure going, and the benefit of getting that going early, which might slow down your excavation below. I think this picture here sort of covers that quite well. So here we've got a picture. This was actually Heathrow T2B, which was built about 15 years or so ago. We can see on the left-hand side there, we've got a diaphragm wall, which is exposed, which has got anchors at the top. And so the bit down on the left-hand side of the picture is showing a bottom-up construction. Built the wall, put the anchors in, excavated down to the bottom. Whereas the bit at the bit in the middle of the picture, where the red barriers are, under the red barriers, is showing a top-down construction for the northern part of that basement. So that basement was constructed partially top-down, partially bottom-up, and so you can see the top-down construction on the northern part on the middle of the slide there. The plunge columns are coming down, so the plunge columns were put in from the ground level. The ground floor slab was cast on top of those plunge columns, and then we're excavating out in between those columns and under the slab. But the superstructure's already flying. The superstructure's away. So if the superstructure is needed to be there while you're excavating below, and that eases the program, that would be the way to go. And I think that nicely shows that, you know, you're obviously down at the basement level in your top down, in your bottom up solution, but you're still excavating because it's much slower in your top down solution, but you have your superstructure already constructed. So the final little piece I wanted to run through was, you know, I say moving on from this, was around plunge columns. And so to enable a top-down construction, you do need to, you know, build yourself plunge columns. And I say they're very common in some of the basement constructions that are carried out in London and other areas where there's a significant amount of basement construction. So these will be done typically in a rotary bored pile. So you'd have a casing in the ground. You'd have excavated your pile down to the level you needed to. You'd have concreted your pile up to the basically your basement level, or your level that you're building your final basement to. You would then put a frame in. So this is a frame that you put in, which is support on your casing, which would help guide the plunge column frame in when you want to put it. So again, temporary works considerations are needed about this to be able to get that frame into the right position. And the frame can be put into quite a tight tolerance, so you can ensure your structural element or your plunge column is lowered into that frame to keep that at quite a tight tolerance. You can see that, you know, plunge columns can be quite big, they can be quite hefty. Obviously they've got gravity which helps them be vertical, but plunging them through that frame down into the open bore of the pile, and then down into the concrete down at depth to support them, and then they're held in position with that frame until the concrete's gone off, and then the frame can be lifted away. So the frame ensures that the column is plunged in at quite high tolerances, so you can get around about 10 mil at the top, 1 in 400 verticality. So those columns can be put in to quite a high tolerance. However, you do have to combine your tolerance of your column with your tolerance of your pile construction, which will come on to the next slide. This actually shows here that, you know, there is a tolerance, and so, you know, as you put your column into the ground, depending on how far below ground you're wanting to cast your floor slab for your initial support, you know, that may well be slightly out of position from where you are at the top, if that makes sense. So your column won't be exactly in the right position, because there will be a certain amount of tolerance. And the key thing to consider, I think, the key thing which needs to be considered more often than not, is the fact that you've got a pile tolerance as well as your column tolerance. So this is quite a complicated little picture here, I apologise, but your black there shows the position, the ideal or your theoretical position of your pile, with your column right in the middle of it in the black. The blue then shows down at the depth of your cut-off level of your pile, so which may be 15-20 metres below the level you piled from, the position that your pile may have moved to based on standard piling tolerances. And those tolerances are difficult to get away from, because you're just, you know, you're digging your pile and you're 30 metres below ground level on a small Kelly bar, so your pile will move out of position. So that may move, and we can see that could move, you know, to the order of 500 mil. We've taken an example there. And your column, when you're plunging your column in, could move in the other direction. So that could move, and we've shown that could move a couple of 100 mil the other way. So because you're using a plunge column to look at your top-down construction, your tolerances of your pile and your plunge column may actually define the size of pile that you're needing to use. So you might not need that size pile for the loading, but you will need that size pile for the construction tolerances of physically putting that plunge column into the right place within the pile. So those things have a significant influence on, you know, how you're designing your piles for your structure. I'd like to come back to this slide, because it's a complicated little slide, and it took me a long time on Copilot to make it work. But hopefully some of that presentation there that I've just been through, and it was fairly a whistle-stop tour of certain foundation solutions, shows how all of these parts sort of work together to be able to develop and to get to the right foundation solution that you need. And really, you know, we should be looking, or should be trying to drive all the time to get all of these elements, you know, working together collaboratively as much as we can, in my opinion. If we carry on, you know, designing or carry on planning construction without the two talking together, we'll come up with a wrong solution, and we won't be managing ground risk in the right way. So with that, I'm going to end, but I'm very happy to take some questions if people have them. Thank you very much.
Brilliant.
I'll leave that slide up.
Thank you. So we've got a number of questions online, and we've also got a couple of handsets. So I don't know, Felix and Rico, if you could give us a hand with the mics. In the meantime, I'll start with the ones online. So the first one from Philip Wilson: should piles be designed by contractor or consultant? I suspect I might know your answer to this one.
No, is this working? Is this on? Yeah. It's a good question, and there isn't an answer. There isn't the right answer, to be perfectly honest. I think it has been done. Well, it is done by both. It is done by both quite regularly, and in fact, in my career, typically it's been the contractor that's been doing the design up to the last 5 years, when lots of the projects I've been working on, it's been an engineered design solution that I've been involved with, to be perfectly honest. So, as I say, I don't think there's a right or wrong answer to that, to be perfectly honest. I think it could be either, depending on the project. Sorry to be a bit vague.
No, thank you. Thank you. Is there anyone in the room with a question? Do you want to wait for the mic so the guys online can hear you?
Yeah, Binod Amate from RSK Geosciences. So in that case, who takes the liability, you know, if something goes wrong? So
In the case of what? In the case of who?
Professional liabilities.
Of who? Well, it depends on who's designing. So if it's a consulting engineer or the engineer is designing the solution, they have the design liability, and then if it's a contractor design, they obviously pass the liability to the contractor to take on that liability. I mean, the benefit of going to the contractor and having a contractor design is that they align their design with their plant and their equipment and their tooling and their experience that they have within their remit. So it aligns with what they physically can build, if that makes sense. Whereas with an engineered design, there is likely to be, or there's more often than not, a little bit of tweaking that's needed from the solution that's developed into what physically can be built based on the plants and tooling that's available. But the liability it's very clear. It's either an engineered design solution sat with the consultant that's on the project, or it's it's past or the contractor has it with their design.
Thank you.
Anybody else in the room?
Ben Marriott, Mont MacDonald. So where the consultant has handed the contractor a design, what are the common things that go wrong for you as a contractor? What makes you pull your hair out?
It makes me pull my hair out more, actually, when it maintains the engineered design and they get to there's a final solution that's developed, which then needs to be modified a little bit to align with the construction process, if that makes sense. So where a contractor picks up a design, as long as the specification is clear and the requirements are quite clear, I think a solution can be developed, if that makes sense, and that aligns. So I think that's why there may be a lot of solutions are left with the contractor design, because people know what they want to support and they know the specification around what they need to achieve, if that makes sense. Just getting a constructable solution to meet that specification is variable. So I find it's perhaps from a contractor's perspective, it's easier when it's past the contractor to design.
Go for another one online. Considering pollution source pathway receptor models, do you have a preferred piling or ground improvement solution for contaminated sites? Again,
A good question. I think that a driven solution, a displacement solution, is better where you've got a contaminated site. If you can get your displacement, if you can get your displacement pile through that contaminated ground. So theoretically, it does create a path. It does create a path as you've driven it through down to the non-contaminated ground below. But that is better than having effectively, if you've got a replacement pile, you're mixing material together. You're starting to mix contamination with with whatever. So I think the mixing process to me is worse than a displacement process of taking a pile through. You do still have to, I say, there is still typically, well, there will still be a path that you could possibly generate, but I would prefer, my preference would be a displacement pile solution.
Thank you. Anybody else in the room, please?
Hi, Ray Hobbs. I'm an offshore geotechnical engineer, so this stuff is unfamiliar to me, except from textbooks and university. Regarding board piles, can you say something about the effect of the bentonite on the skin friction that you can generate, and also about how reliable end bearing might be, or displacements required to mobilise it, given that you can't really be sure that you've got a very clean base? The stuff's going to fall off the side of the hole.
Well, possibly 100%. So there is. I mean, the longer you leave bentonite in a pile bore, the more the filter cake can build up, the more reduction you theoretically get with your shaft friction. So there is a reduction in shaft capacity by leaving bentonite in the bore for a lengthy period of time. For the onshore stuff, I mean, piles, rotary board piles that are constructed under bentonite typically have a factor, typically reliance on the shaft friction rather than the end bearing for their serviceability limit state. And so that means the end bearing is important for overall fracture safety, but it's not so important for for the settlement criteria. Doesn't mean you shouldn't be concentrating on getting a clean base. So there are methodology for cleaning out the base, making sure your bentonite is at the right the right levels of sand content, making sure that there's not material falling down through the bentonite to the base. So the processes are in place to clean out the base and then to assess the base with your various different methods, even of basic as tapes dropping down to with weights on to ensure that the base is solid, if that makes sense, to ensure you've got a base capacity which works. And then clearly, the backup to that would be the testing or the working pile tests that you carry out on a number of piles to demonstrate its serviceability limit state. At least you've got the settlement criteria that you need. So no, there is an impact, and the sort of the key question, or the question that's being posed at the moment, is there such an impact using polymer as there is with bentonite? And I think that's a question that is worthy of investigation. And my experience is also showing that using polymer, you don't get so much of a shaft reduction as you do with bentonite. So using a polymer support fluid, if you're leaving piles open for a longer period of time, is more beneficial than using bentonite. But there is further work still needed on that to justify it and to be really firm with it. Thank you.
I've got another one. One of the things we do offshore, because of the effect on the marine mammals and fish even, is noise reduction. Is anything done onshore to reduce the noise level for pile driving?
So yes, is the answer to the question. So it can be. So you can shroud. You can put sound shrouding around because the driven piling is really more noise. Is typically more noisy than the rotary piling. It's interesting with rotary piling, the biggest noise seems to come from when you're spinning off and you're getting clanking of steel on steel rather than when you're drilling piles. But for the displacement piles, the driven precast, the driven steel piles, yes, you can shroud, and it does minimise, and it does help the noise.
Go for another one online. What are the typical defects in diaphragm walls, and how are they rectified?
Could go on for a long time. So I think some of the big things with diaphragm walls, so obviously the joints are a key issue with diaphragm walls. So you put your stop ends in, as we've seen with the water bar, and there are various different types of stop ends you can use that you peel off or you jack out or do whatever. But they're a source of issue of whether you can get whether the water bar gets into the right place, whether the stop end peels off properly, or you get a leak or your water coming through the joint. And a typical remediation around that is you can inject or you can put a sealing in around those joints if you get any water ingress through the panel joints. The other one you can get is mattressing effect, or really concrete that isn't flowing through the reinforcement. So again, this is an issue about having if your wall's too thin, so your steel is too dense. If you've got a thin wall, you might have to put a hell of a lot of reinforcement in there. If you've got a hell of a lot of reinforcement, your reinforcement gets too congested. It gets more congested at splice locations and things like that. So the concrete doesn't flow adequately from your tremie through your pile cage to the surface of the wall. And so as you excavate down, you're exposing areas where the concrete hasn't flowed through properly, and you see parts of the reinforcing cage. And again, the remediation of that is only breaking out and recasting in remedial areas of that of that wall. But the solution around that really is to ensure, one, you've got a good concrete mix that flows properly, and two, you've got a diaphragm wall cage which is designed with adequate spacing in it to allow concrete to flow. So I think, from my perspective, they would be the two main areas of defects. There could obviously be a lot of others, but I'll stick with those two at the moment.
Brilliant, thank you. Any more from the room?
Hey Mark, Kevin
Hello.
from Stantec. Great presentation. I guess my question is also related to the whole support. I was keen to understand what are your thoughts around choosing between temporary liner, bentonite, polymer, and even with a temporary liner. I understand when you withdraw the liner, it's not actually that straightforward process. Even though we say that we can withdraw it, reuse them. Can you hear your thoughts on that? Yeah.
So again, it's ground condition dependent and length of temporary casing dependent. So you've got, there is a limit to the amount of casing that you can physically put in and then sensibly extract, if that makes sense. So you put a bit of casing, you leave it in the ground. The ground obviously, it doesn't stick. It's sort of, it glesses around that bit of casing. So it takes a little bit to keep it moving, or to be able to move it out at the end of the day. So you don't want your casing to be too long that you physically can't extract it, if that makes sense, because you'll be in a, that would be a mess. So you would, and also you wouldn't want a bentonite farm or a polymer farm on a site where you've got no space to put it. So if you've got a very congested site which has got a sensible length of casing that you need, you'd rather go for the casing, if that makes sense. If you've got a site with a wide area that you could put a bentonite farm up quite easily, you might choose to limit your casing length, because that would be easier to extract and put in, and use your bentonite quite regularly to construct your piles. So it's a combination of being able to input and extract your casing, and a location and a sensible place to put your support fluid farm to be able to work it sensibly. So it doesn't really answer your question very much.
Thank you. Any more questions from the room? Okay. Go ahead, please.
I wonder if you've ever come across timber piles in your career. If not, do you think in the future we may see more of them, given the sustainability drive and so on?
It's a good question. I haven't had any timber pile. I haven't been involved in a project where we've used timber piles. I have been involved in projects where timber piles have been discussed at feasibility stage or optioneering stage, and then for one reason or another we've not quite been brave enough, I would suggest, to say let's go back to using timber piles which were put in, we have been used quite successfully previously. So no, so I haven't first answered your question, but yes, I think there would be. I think there will be a time where if environmental or sustainability decisions are driving what is needed for foundation solutions, the timber may well, it's going to be a trump card, isn't it? It's going to be coming in. We're not using concrete, we're not using any of that, any carbon costly material, we're using timber. It will be a big tick in the box. So I think there will be areas where that may well come back in. Yeah.
Thanks.
Also, I'll just add to that, maybe there could be, other synthetic materials could be developed, different to concrete, to be used in piles. And they are used, they can be used at the moment.
Brilliant. Any more questions in the room? I think that's it from online. So.
Yeah, this is Tim from ACOM. So you just briefly touched on about support fluid as well. So just want to know more how you choose between bentonite slurry and polymer fluids, and from experience, like what are the challenges with using polymer fluids specifically with relative new technologies? And
so again, a tricky question in some respects, because it isn't a straightforward answer, but because they work very differently, to be perfectly honest. So polymers are obviously man-made; they're synthetic material. They work by having strings effectively in them, which work together. Whereas a bentonite creates a filter cake on the edge of the on the edge of the pile or the diaphragm wall to support it. So within the UK, my experience is it has been more typical to use bentonite, particularly constructed, because the use of polymer hasn't been really taken that far to use in diaphragm wall construction. There have been recently. There've been some we use polymer on Old Oak Common Station, for example, for the diaphragm wall, but that was in a very friendly ground condition in London clay. So polymer is more environmentally friendly, because you can dispose of it more easily. You can make it inert in a better way, but there's still quite a lot to learn about it and make it work properly in all pile types, I think. So there's a bit to learn. The States use it a lot more than we've used over in the UK, but it is becoming more and more common and popular. So I think polymer will take over, in my opinion. I think we will understand the use of polymer. We'll understand the chemistry behind it. Some people in this country understand it very well, more than others, but I think it will be. I think polymer will take over from bentonite, because we'll be able to manufacture it and use it better. If that answers the question in any way.
thank you.